Okay, so in this section, we will give another example of convergence of stochastic processes on a space of continuous functions, and it will be convergence of the so-called empirical process to a Brownian bridge. Now, before we state our main result, we will begin with some motivation. So we start by considering some IID sequence of random variables, xi, and then let f of t be its cumulative distribution function. Okay, so for t on the real line. Now, let's also denote by fn of t the proportion of xi's that fall below t in the sample from 1 to n. So fn of t will be just 1 over n, sum from 1 to n of the indicator that xi is below t. And this proportion is called the empirical cumulative distribution function. Okay, then by the strong law of large numbers, of course, this average converges to the expectation, which is exactly the CDF, right? So for any given t. Okay, so if you fix t, this is just the straw of large numbers because the expectation of the indicator is the probability, which is the CDF. Now, by the central limit theorem, right, if you scale by square root of n, then you will have convergence to some Gaussian distribution. Right, so if you multiply the difference between the empirical CDF and the limit, which is the CDF, for any fixed t by square root of n. Now, of course, you can rewrite it also as 1 over square root of n, the sum from 1 to n of the indicator minus its expectation. Then we know by central limit theorem that this converges in distribution to some Gaussian, or its distribution converges to Gaussian distribution with mean 0 and variance given by the variance of one term. Of course, the variance of indicator is just its p1 minus p. So p is CDF and 1 minus p is 1 minus CDF. All right, so this is for any fixed t. But next, we are going to try to look at this uniformly over t. And the first thing we notice is that by monotonicity of the CDF, if you look at the supremum over all t of the difference between empirical CDF and the limit, which is the CDF, this actually also goes to 0 as n goes to infinity almost surely. And this is left as an exercise at the end of the section, but it's a simple exercise. And then we can ask, what can we say about the supremum on the scale 1 over square root of n? So just like in the central limit theorem, what if we multiply it by square root of n? Okay, so we can ask, does this converge when n goes to infinity in distribution to something, right? Is there a limit of this distribution? And so that's the question that we are going to study here. And from now on, we will consider this question in the case when the CDF is continuous function. So we'll assume that CDF is continuous. And the reason for this is because it turns out that the answer will not depend on the CDF as long as the CDF is continuous. Okay, and this is the basis for the so-called Kalmagorov-Smirnoff test in statistics. Okay, which we will come back in the next section. But indeed, to see that the distribution does not depend on the CDF as long as it's continuous, you can simply make the change of variables as follows. So if we consider this supremum above, first of all, let's write something which is maybe not automatically completely correct, but we'll give a justification of this in a second. So what I want to do here is, inside the indicator, apply a function f to this inequality xi less than or equal than t. And so write f of xi less than or equal than f of t. Okay, now, if function f is strictly increasing, this is fine, but sometimes the continuous CDF can have flat parts, so this is not quite correct. But when you have a flat part, that means the probability of that interval is 0. So you can also see right away that this is still correct with probability 1. But actually, after we now make the change of variables, what we wrote will be clear by just a different, more direct consideration. So what I want to do is now replace f of t by s. So make this change of variables s equals to f of t, okay, which is now between 0 and 1. And so write this supremum as supremum over s in 0, 1 of the same difference or the same expression as above. Okay, and because f is continuous, f of t will take all values in between 0 and 1. Now, you can see a little bit more directly without really thinking about this middle step that you can go directly from the first to the last equation here. Okay, and the reason for this is if you consider this difference here that you are trying to maximize, and here I forgot factor square root of n, but this difference that you are trying to maximize, the first term is increasing and it's just a step function where you jump by 1 over n at every xi. And the second is just decreasing linear function. So it looks something like this. You have decreasing function, then at some point x you jump by 1 over n. And then until you hit the next point you are decreasing, and then you jump by 1 over n, and so on. So this difference looks like this. And you can see that on each interval between the two jumps, the maximum can be achieved only at the end point, because it's just a monotone function on that interval. It's just decreasing. And the jumps here occur at points in this last expression, at points f of xj, right? So in particular, if you take such value f of xj, for s to the left of this, right to the left of this, you only have seen j minus 1 points before that. So the first proportion will be just j minus 1 divided by n. While the second continuous term s to the left of this point, well, it's going to be f of xj in the limit when you approach this point because of continuity of the second term. And as soon as you jump, the first term becomes j over n, while the second term is still f of xj by continuity. So as a result, this last supremum will be just a maximum of absolute values among all these values before jump and after the jump. So you just have to look at finitely many possibilities. But then if you look at the top expression here, it's the same thing. You have the points that you consider are xj instead of f of xj, and then right to the left of the point number j, you have seen j minus 1 points. But the second term is f of xj right to the left, but by continuity it's still f of xj. And the same right after the jump, by continuity you compare it with f of xj, so it's exactly the same values. So as a result, you have this representation in terms of f of xj after making the change of variables. But now let's notice that because f of x is continuous, or f of t is continuous, we know from chapter 1 that when you plug in a random variable into its CDF, let's denote this by little xi. When we plug in random variable xi into its CDF, right? We know that these are actually uniform on 0, 1. So they have uniform distribution on 0, 1, right? And so the above supremum now can be rewritten as the supremum over S on 0, 1 of the same expression as above, except now we'll just, instead of f of xi, we'll write xi, and these xi are now uniform on 0, 1. And so you can see that this expression now becomes independent from the CDFF, right? In the sense of the distribution, right? The distributions of these little xi's are uniform, so there is no longer any reference to the CDF. Now let's write this final expression as a supremum over t. Now I'm going to go back to the variable t just for convenience of this process x and t, where now the t is just, I renamed s into t, so t from now on will be between 0 and 1, and this process xtn, so I just introduce this notation here for the above expression, so 1 or square root of n, the empirical CDF for the uniform sequence minus the CDF for the uniform sequence. And so this process here, okay, it's called empirical process. Okay, and our goal in this section will be to show that this process converges to a Brownian bridge. First of all, by the central limit theorem that we already mentioned above, just specialized to this uniform case, right? That's exactly the scaling in the central limit theorem. So for any fixed parameter t, this will converge in distribution to, or its distribution will converge to Gaussian with variance given by t 1 minus t. But we can see that finite dimensional distributions of this process, if you pick finitely many times t, let's say t1, tk, you will also have convergence to some Gaussian vector by the multivariate central limit theorem. You just have to calculate what the covariance is. Okay, so these are already centered, and if you take, let's say, 2 times s less than or equal than t, right, then you calculate the covariance of xn at time t and at times s. Well, it will be just expectation of their product. Okay, and when you multiply out the sums above, the terms with I not equal to j, they will disappear, right? Because those are just independent and mean 0. Okay, so you will only have the sums for I equal to j left, and they will all be actually the same, right? So if you look at one term, it will be indicator that x, let me write 1 here, less than or equal than t minus t, times the same term for s. So indicator that x1 less than or equal than s minus s. Now you will have the sum of all these terms over xi instead of x1, but the scaling will be 1 over n, and so those will just average to the same constant here. Okay, and then when you multiply this out, the product of 2 indicators will be just the second indicator, because we assume that s is smaller, and that will give you just the probability that x is less than s, which is s. And then the other ones will be minus st plus st. So actually this will be just s1 minus t. And now we should recognize that actually this is a covariance of a Brownian motion. So by the multivariate central limit theorem, we know that our process xn at finitely many times will converge in distribution to a Brownian bridge at the same times. Okay, where this process Bt is a Brownian bridge. Okay, and what we want to show is that not only finite dimensional distributions converge, but these processes converge as processes on the space of continuous functions. So let me state the main theorem that we want to prove here, right? Namely that this x and t for t on 0, 1 converges in distribution to Brownian motion for t on 0, 1 on the space of continuous functions on 0, 1 with the sup norm. Now, of course, you should notice here that something is not quite right. So this theorem is a theorem with an asterisk. Namely, if you look, the processes x and t, they are not continuous. They don't live on this space of continuous functions. However, if you recall their definition, then you will see that these processes here, they have jumps. So x, tn, they have jumps which are 1 over square root of n by our scalings. And in between the two jumps, it's just a linear function with the slope minus square root of n. Piecewise linear in between with slope minus square root of n, but the slope doesn't matter to us here. The point is that the jumps are 1 over square root of n, and in between it's monotone or linear. And that means that you can actually, so if you look at the graph of this, so you have some linear piece, and then you have a small jump, 1 over square root of n, and you have another linear piece until you see the next jump. And as a result, you can define a continuous version of this process, which is uniformly close to our process xn. So for example, you can just take a middle point in these two intervals and connect the value of the function in between, right? And as a result, if you do this for every interval, this will define a process, let's call x tilde and t, which now will be continuous in t. And moreover, the difference between x tilde and x uniformly, right, in the sup norm, this will be bounded by the size of the jump, which is 1 over square root of n. So we have to understand the above theorem for some continuous modification which is uniformly close to our original process. Okay, but the reason I stated it for xn is because both in the proof and in application you can immediately go from xn tilde to xn just because of this uniform control of their difference. So for example, when we prove the above theorem for the continuous version for x tilde, we need to show uniform tightness, and by the result in the previous section, it's the same as controlling the modulus of continuity. So the main thing that we need to show in this section is that the limit when delta goes to 0, the lim sup when n goes to infinity of the probability that the modulus of continuity of your process at delta exceeds epsilon, this goes to 0. Right? That's our main goal. Okay. However, again, you would like to prove this for the continuous version for x tilde, but I'm writing directly xn instead of x tilde because, well, if you consider the modulus of continuity of one of them, it will be within 2 over square root of n from the modulus of continuity of the other. Right? And so as a result, this statement for the modulus of continuity will be equivalent for both, and so we don't actually need to redefine our process, so we'll work directly with the process above. Also, when we apply this theorem that you have convergence of the processes on the space of continuous functions, it implies that if you apply to your process any continuous function on the space of continuous functions, you will also have the corresponding convergence of distributions. So for example, if you take a supremum of your process or a supremum of absolute values, this is of course a continuous function on the space of continuous functions with this norm, so automatically from the above theorem you will have convergence in distribution to the same functional of the Brownian motion. And again, in this statement on the left hand side, whether you put x and tilde first, you know that the supremum is within 1 over square root of n, so the statement for the continuous version automatically implies the statement that we want for the process x. Okay, so as a result, I'm not going to redefine the process, and so from now on we'll just focus on proving this statement here, the control of the modulus of continuity. Now, to prove this statement, we will actually immediately apply Chebyshev's inequality, and instead of controlling the probability, okay, so we'll just bound this by 1 over epsilon times the expectation of the modulus of continuity, and in the rest of this section we'll control the expectation instead of the probability. And this will be done in 2 main conceptual steps. But first, let's rewrite this modulus of continuity a little bit more explicitly. So by definition of the modulus of continuity, okay, it's just a supremum over all t and s within delta from each other of the process at time t minus the process at time s. Okay, so this will be the same supremum, and then when you subtract the average of indicators, you will just have the average of the indicator of the interval in between these points. So let's suppose s is smaller than t, then the average of indicators will be again an indicator of this interval. Right? And then the difference of CDFs will be just t minus s. And we also have a square root of n factor. And then before we start the main steps of the proof, let's actually simplify a notation for a second and replace these indicators just by, or call these indicators a function f. So this will be a supremum over all functions f of the average of f of xi minus the expectation of f, where in this particular case the function, this class of functions that we are looking at, are just the above indicators. Okay, so f of x is the indicator of the interval from s to t, right, where we choose s less than t within distance delta from each other. Okay, but the reason that we rewrote the above empirical process in terms of some class of functions is because the main steps in our proof will be quite general. So they will apply to more general classes of functions, and only at the very end we will come back and deal with this particular class of functions. The rest of the proof will be divided into two conceptual steps. The first one will be a symmetrization argument, and the second one will be the so-called Kalmagorov's chaining argument. So the symmetrization argument will be the following very simple, but at the same time, as we will see later, a very crucial observation. So if we consider the expectation of the supremum above, and here again we are going to consider sort of arbitrary set of functions as long as they are bounded, so everything is well defined. So we compare the averages of f of xi with their expectations, and the first thing that we'll do is to represent the second term, or the expectation, as expectation of another average. Okay, so the first term will be the same, but the second term we are going to write it as an expectation of the same average, where instead of xi we will consider some independent copies of xi. So xi prime will be just some independent copies. So it will also be IID uniform, in other words. Now, once we write it like that, we can actually take this expectation here outside of the supremum or outside of the absolute value first, and then outside of the supremum by Jensen's inequality. And we can write that this is less than or equal the expectation, okay, where we do not write the expectation inside. Okay, in other words, the expectation on the outside is both in xi and xi prime. Next, we notice basically by symmetry, then when you write the supremum here, you can put any sign in front of this difference. So here you can put either plus or minus f of xi minus f of xi prime, where the choice of the sign can be whatever you like in front of any I. Right? So some of them can be pluses, some of them can be minuses, and this does not matter because putting a minus sign, it's equivalent to just switching xi with xi prime. But this pair xi prime, they are just independent copies of each other. So if you switch them jointly, they still have the same distribution and independent of all the other xi's and xi primes. So putting a minus sign, it's just like renaming this pair. So it doesn't change the distribution, and since you're looking at the expectation, it doesn't change the expectation. And because this is true for any signs, you can put random signs and average over them. Right? So this will be equal to the expectation over epsilon, where epsilon will be some random plus or minus signs in the above expression. Okay, so in here, instead of plus and minus, I put epsilon I taking values plus or minus 1. Okay, and their distribution can be whatever you like as long as they are independent of xi's and xi primes, of course. And then we'll just use triangle inequality to separate in this supremum xi's from xi prime. So by triangle inequality, you can write the term with f of xi plus the same term with xi prime, but since they have the same distribution, it's the same term. So this simply results in a constant 2 in front. Okay, and again, up to here, the choice of the distribution of the random signs is arbitrary. They can even be correlated. But from now on, we will take these epsilon 1, epsilon n to be IID Rademacher random variables, which means that they take value plus and minus 1 with equal probability 1/2. Okay, and this completes the symmetrization step, and we will see later on why introducing these Rademacher random variables is so useful. Okay, it will basically be because of the Hovding's inequality. We have a very good control by Hovding's inequality of averages of Rademacher random variables. Now, from here, one can actually finish the proof very similarly to what we did in the last section when we talked about convergence of rescaled random walk to a Brownian bridge. So, and in fact, there is an exercise at the end of the previous section which outlines how to finish this proof. But instead, we'll do something a little bit more general than again applies to more general classes of functions, and only at the end we'll use a specific class of indicator functions in this particular case. And so in the second part, we will prove the following result regarding these Rademacher averages. So first, we are just going to fix our uniform random variables x1, xn. So we'll just treat them as constants for a second, and then we'll denote by f the vectors in Rn given by evaluating our function f on x1, xn, when f belongs to a class of functions that we are interested. Okay, and since x1, xn will be fixed, in this part we will simply view the elements of this set f as vectors with coordinates f1, fn. And in the case of indicators, this will be, the coordinates will be between 0 and 1, but we'll assume that they are simply bounded, and for certainty we'll just assume that they are bounded by 1. So this is a subset of a cube with sides -1 to 1 in Rn. And in the second part, we will prove the following result. So here I'm just going to finish the proof of the main result by just taking as a black box what we will prove in the second part. And so what we will prove is the following. Okay, we'll prove that when you take this supremum over the set f inside your cube of the above so-called Rademacher process, and remember right now we also have the scaling by square root of n, so here I'll bring it back. So 1 over square root of n times the sum of epsilon I f of xi, which is now denoted just by fi. This supremum, and because x's are fixed, here I'll take expectation only with respect to this Rademacher random variables. And so the main calculation or the main result in the second part will be that this will be bounded by some absolute constant integral from 0 to dn of the square root of log of some constant over u du plus dn, where dn squared will be the supremum over all f in our set of 1 over n sum from 1 to n of fi squared. So in other words, here you just take the Euclidean norm of your vectors f, over which you maximize squared, and you normalize it by n, and when you take supremum you get dn squared, or when you take the square root you will get this quantity dn. And actually, we will prove a more general result which will apply to any subset of a unit cube on Rn, but when we apply that result to a specific functions given by the indicators that we are interested in, right, the result will reduce to this particular inequality. Okay, but before we take a look at that, let's see how we can finish the rest of the proof of the above theorem. Okay, first of all, in our case, the supremum, we'll recall it's a supremum over all s minus t less than or equal than delta, and then the function is just an indicator, so indicator squared will be just an indicator of xi between s and t. And so if we recall what we did above, we started with the expectation of the modulus of continuity of the process xn. Then we did some symmetrization, and then in that symmetrization, the expectation in the random Rademacher random variables or random signs was bounded by this constant times the integral from 0 to dn. I'm just rewriting this, the above bound here. Okay, but remember that the expectation here on the left hand side also involves random variables xi, the uniform random variables that were fixed for a moment. So here we actually have to take the expectation in these random variables xi, which still appear in this definition of dn. Although this is not very important, but it's just a little cleaner to notice here that when you look at this integral as a function of the upper limit, this will actually be a concave function of the upper limit, because the derivative will be the square root of the log of 1 over u, which is clearly decreasing in u. And because as a function of the upper limit this integral is concave, you can take expectation inside by Jensen's inequality. So by Jensen, you can write the above bound as k times integral from 0 to the expectation of dn plus the expectation of dn. So we have to see what this expectation of dn looks like. But now let's recall that this dn squared in the particular case of indicator function, so let me just copy from what we wrote above, it's the supremum of the difference of indicators. So again, the indicator can be written as the difference of indicators, so I'll write it as average of indicator that xi is less than or equal than s minus average of indicators that our uniform xi is less than or equal than t. And we already mentioned above that will be an exercise to show that these averages here converge uniformly, okay, basically by the strong law of large numbers to their expectations. So the first average will converge to s, and the second one will converge to t. This convergence is actually uniform, so as a result, this supremum here will converge almost surely to the supremum of s minus t when their difference is less than delta. So this will be delta, and this convergence is almost sure. So as a result, dn converges to square root of delta almost surely, and notice also that this dn is bounded. So by the dominated convergence theorem, expectation of dn converges to square root of delta. And so if we go back in the above bound, right, when you take a limit n goes to infinity, we get that the lim sup when n goes to infinity of the expectation of the modulus of continuity will be bounded by some constant times integral from 0 to square root of delta plus square root of delta. And finally, we want to take the limit when delta goes to 0 in order to conclude this uniform equicontinuity, or to conclude that the sequence of our processes is uniformly tight. But this is clear here that both terms on the right hand side go to 0 when delta goes to 0. And so as a result, this finishes the proof of the main result of this section. If we can show the control above here, if we can show this inequality here, and so in the second part we will prove a more general result for these Rademacher processes, and then this result for the particular case of functions that we are interested in, for these indicators, we'll see that it reduces to the inequality above.